Welcome, class, back to Advanced Aircraft Systems. I'm your instructor, Tom Mahoney. And guess what? We're getting close to the end. We have this module or this lecture and one more lecture after that. Then we have completed the systems training for this particular course. So let's go ahead and get started and continue with ice and rain protection on the CRJ 700. All right. Ice and rain protection systems allow for the operation of aircraft in heavy rain and icing conditions. So, of course, we're a commercial aircraft pilot, so we cannot just be held up for ice or rain or sleet or, that old little thing they used to talk about at the post office, So we're going to try to get going. Now, there is a caveat to that. We do not fly in thunderstorms. No aircraft, other than maybe if you're one of those hurricane guys that like to fly out there, look at the eye of the hurricane, and they're, I don't know, whatever it is, a C-130 or something like that, hurricane airplane. But we do not fly our commercial jets or your light private airplanes into thunderstorms. So that's out of the question. But we try to take on any other kind of adverse weather that we think we can handle without jeopardizing safety for the flight. So we talked about earlier what we use bleed air for. Of course, bleed air in this case, as we remember from our bleed air training, bleed air comes from the compressor section of the engine. And there are two sections usually. There's a low section or a high section or a mid section, whatever the case might be for that specific engine design. But that bleed air is hot. So we use that hot bleed air to our advantage, and we use it for, at least on the CRJ 700, for anti-ice and de-ice of both the leading edge wing or the wing leading edges, and also for the engine intake cowl. We also use the electrical system that is used for heating the flight deck windshields, the flight deck side windows, air data probes, and sensors. So what are we actually talking about? Well, we're talking about the leading edge of the wings, and we all should know what those are. That's this area right up in here. We want to make sure that those remain clear of ice. We do not want the leading edge of the wing getting coated with ice. That would disrupt the smooth airflow of the air over the wings, thus reducing lift. That would be not a good thing. We also do not want anti-ice on our engine, leading edge of the engine nacelles, because if they get coated with ice, that ice could break off and more likely than not be ingested into the engine and possibly do damage to the engine. Remarkably, on this aircraft, we do not heat any of this part of the elevators, the stabilizer, horizontal stabilizers, or the vertical stabilizer. The DC-9 I was on, we actually did heat the horizontal stabilizer. The 737 does not heat the horizontal stabilizer or the vertical stabilizer. So in this aircraft, it's much like the 737. So apparently it's passed all the certification requirements for flying in non-icing. So they apparently do not need to worry too much about that. Apparently it does not affect the aerodynamics of the aircraft significantly. Of course, we did mention flight deck windows are heated electrically right there. And we have all these probes and sensors on the side, each side of the aircraft. Of course, that's providing the pilots with information. Our flight computers need this information to be reliable. And so without keeping those heated almost at all times, we take the risk of having them ice up, and we certainly wouldn't want to have that. So the panels that control the anti-icing systems on the aircraft are the bleed air panel, which is located on the overhead panel in the cockpit. That's this panel right here. We would normally have this switch in the normal position for normal operations. We'll talk about that panel a little bit more in following slides. We have the anti-ice panel itself, which is a panel that the first officer will pre-flight verify that it's set up correctly before we take off. And if you'll notice, we have the wing anti-ice switch here. That's actually a bleed air switch that's going to duct heat to both the left and right engine. Just takes one switch, and we can accomplish getting bleed air to the leading edges of both wings. Then we have anti-ice for the cowling. Engine cowling is what we're talking about. We have the left-hand cowling. You see that there, and the right-hand cowling. So it takes two switches here, and those again are bleed air switches. So you can think of everything up here as being bleed air related. So engine nacelles, cowling, two switches, wings, just one switch. Then we have the switches down here. Think of these switches as being electrical switches. And in this case, we're talking about the windshield heat, and it's an electric switch for the left-hand windshield and the right-hand windshields. And then, of course, we have the probes that we turn on, and they'll be on or off. Now, you do need to notice that the windshield has a low and a high position and an off or reset position. So it's a 3-position switch. We'll talk more about that. We have 2 wiper switches, okay? Remarkably, the wiper switch, each wiper switch controls both wipers on the aircraft. So it just kind of depends who's going to turn the wipers on, turns their associated switch on to operate both wipers. Kind of a weird thing. I've never seen an airplane wired quite this way, but don't forget, this is a Canadian design. So they have pretty slick engineers. I'm sure there's a reason or a thought process that they went through to accomplish that or to set the switches up in that manner. We have system monitoring on this aircraft for the anti-ice. We have an anti-ice synoptics page, just like we have on most other systems. We can go down to our synoptic selector switches and pull this up, the synoptics page up, so we can see what the anti-ice is actually doing as it relates to bleed air in this case. So this is where the bleed air comes from on the page from both sides. We have our isolation valve here. And of course, when we put that one switch to the for the wings to the on position, we're going to be able to de-ice both because that one switch operates both of these valves. And of course, we have the valve here for the left-hand cowling for the engine, and this one valve here for the right hand. And that's those 2 switches we looked at previously. If we do have a situation that occurs, we'll get some sort of alert depending on what the situation might be. In this case, it shows that we have a magenta or red alert, and that is a serious one. We're probably getting a master caution. Actually, a master warning light comes on when we get something like this. So it's saying, hey, wake up, guys, take care of this situation before it gets out of control. So we get our QRH out and read and do as it would be a checklist to read and do. Other parts of the ice detection system include a detector unit. Somewhere located in the compartment, I would imagine. And then we have a probe out here on the right and left side of the aircraft in this area right here. And what that probe does is it actually detects ice as ice would form over the top of that probe. And I imagine this probe has a vibration characteristic so that when there's no ice, it vibrates slightly. But then when it gets coated with ice, the ice stops the vibration, and then we would get an alert. We didn't used to do it that way on the old stuff I used to fly, like the old DC-9 or even the 717 or 737. We actually looked out at the windshield wiper where it pivots. There's a little bolt that comes up through the windshield wiper. And on the top of that bolt is a nut and we would look for icing, ice that would be forming on that nut. Of course, when we saw ice forming on that nut, then we'd know that we probably have ice forming on our engine nacelles as well as the leading edges of the wings. So we would know, let's get some anti-ice turned on. We're obviously encountering icing conditions. So that's how we did it back in the old days. But this aircraft is using some newer technology, which is fine, should work and keep you out of trouble. We have an ice detection test that we do. So we obviously want to make sure our systems are operating and functioning normally, because we fly these aircraft at high altitudes in below freezing conditions. And if you enter a cloud, whenever you're at those freezing temperatures, you're almost guaranteed to probably start picking up ice whenever you're in a cloud. So cloud below 30 degrees, obviously there's going to be ice. It can actually form at, say, as high as maybe 10 degrees above freezing if you're in a cloud, because of the aerodynamic pressures around the engine nacelles and the wing and on other components. So depending on what airline you're working for, which airplane you're flying, they're going to tell you when they want you to turn that anti-ice on, at what temperatures. Some airlines, it's 6 degrees above freezing. Some companies, I can remember, did 8. It seemed to vary with each of the companies I flew with. So just do what the company says to do, and that's a policy, and that's how you'll operate their aircraft, because they own it, they're paying for it. You just get the joy of flying. So ice detection and air data sensing and heating units are tested using the, oops, went too far. Let's go back. There we go. Okay, ice detection and air data sensor heating systems are tested using the detect test switch light and on the anti-ice panel. So we've looked at this panel briefly before. So there's that panel. This panel happens to be, by the way, on the first officer's side of the aircraft on the overhead panel. This is a panel the first officer will pre-flight. So this is what the first officer is going to do as part of his pre-flight for this panel. He's going to push this switch light switch button, and normally it's dark, has no coloring to it. If the temperature is below, at or below 30 degrees, you're going to push this and you're going to get an amber light color on your switch. You have to hold it down for 5 seconds to get all this to happen. Yeah, so you hold it down, you're going to get an amber color on the switch if you're 30 degrees or below, and then you're going to get a master caution, ice and amber, and ADS test. So you're going to be sure to check all this stuff out when you are doing these tests. I believe I have a better slide of this later on, and if not, when we get to another slide, we'll explain this in a little more detail. So let's look at some of the switches here. There is no, the testing that we're doing here is for the whole panel when we push that switch. The other thing you're going to do when you're setting this panel up as a first officer, if the temperature is, and I may have said 30 degrees here, what I meant is 19 degrees. If you're 30 degrees here, you're going to put it on low, these switches on low. But we'll cover that here in a slide coming up. You've all seen this schematic. This is your bleed air schematic that we've talked about before. As you can see, things haven't changed. We're still getting low pressure bleed air from the 6th stage and high pressure bleed air from the 10th stage on the engines on the CRJ700. This is our primary valve here for opening and closing to shut bleed air off going to the leading edge of the wings, or turning bleed air on to be able to anti-ice or de-ice the leading edge of the wings. This valve here opens and closes with each with its own respective switch on the anti-ice panel to heat heat up the leading edge of the engine nacelles. Anti-ice and leak detection controller, the AILC. So, of course, as with all systems we have on this aircraft, there is a monitoring computer that takes a look at things and tells us what's going on. The AILC actually detects whether or not we're getting enough temperature to the leading edge of the wings. In this case, we have some temperature sensors right here. And over on the right wing, and those are wired into the AILC, and it's going to tell us automatically if we have a low temperature in the leading edge of the wings. We can have a system failure. If we were trying to provide bleed air to the leading edge of the wings, for example, of course, we can look at our bleed air panel, and we know it's a bleed air panel because it says bleed air right here. Most of the panels in this aircraft that I know of all tell you what that panel is about. In this case, this one's about the bleed air. In this case, normally we would have this switch in the normal position right here. But if we have a failure in the system for any de-icing the wings, anti-ice for the wings, for example, let's say this valve here failed to open when we turned on the wing anti-ice switch, then we would get an alert and we'd say, hey, you've got a failure here. You need to do something about it. We, of course, would get the QRH out because it would no doubt be either a magenta or an amber alert. And then the QRH would direct us, in this case, to take our bleed air switch from normal to from left side. And that basically means that since this valve would have maybe failed closed, we're going to go ahead and open this valve and allow bleed air to come up and cross over to heat the leading edge of the right wing as well as the leading edge of the left wing. So that's what this switch here does. Kind of interesting. But I'm sure the QRH will drive you to that. So, you know, it is what it is. A lot of things could happen. We could have had a bleed air valve down here fail. That would result in basically the same issue that this is. And that's why we need to have this alternative wing anti-ice cross bleed valve in the system so that we can continue to de-ice the leading edge of the wings in the event that we are in icing conditions. So we have a wing overheat alert. This is a serious condition. Wing overheats can actually get so hot that it can deform the leading edge of the wing. You would never actually even run your anti-ice, wing anti-ice on the ground on certain airplanes. For example, the DC-9, we would have those turned off anytime we were on the ground because we wouldn't have enough airflow going over the leading edge of the wing to dissipate the heat. The heat would build up and then deform the leading edge of the wing. Not something we really want to have to fix on multi-million-dollar aircraft. So we would get an alert like this, a wing overheat. Of course, this is magenta. We probably get a master warning light. And of course, that would drive us to get the QRH out and follow the QRH procedures to take care of the issue. All right, engine anti-ice. Let's talk about that for a little bit. We mentioned earlier that this is the valve that opens and closes to provide anti-ice to the engine nacelle. When that valve is closed, as it's shown over here, there would be no bleed air to the cal anti-ice system here. So this would be cold, this would be hot. Not really that complicated. So let's take a look at our switches up here. As you can see, the anti-ice here on this panel has the cal left-hand side turned on. That's what we have the on down here for. Of course, I can't swipe over. Here it is. It's on right here. So the switch is shown in the on position. That's what drove this valve to the open position. This switch here is still in the off position, and that's why this valve is remaining in the off position. If you pulled up your synoptics page for engine anti-ice, you would notice that we have the valve showing open here as it corresponds to our schematic over here. And of course, this one is closed as it corresponds to the schematic here. And of course, we would get an indication. Now, this is a green indication, right? So that's just like things are working correctly. The position of the valves match the position of the switches. So in this case, where we have the left switch in the on position, it's saying to us that yes, this valve and this switch are matching. So it's a comparison and it's in green, so things are good. And of course, whenever it's in white, that's just to alert us that we happen to have the seatbelts on and the no smoking signs on. So the colors mean certain things on this aircraft, but for now we're talking about the systems, and the color in this case is green. That's just saying, hey, the switches compare properly to where the switches of the valves are. We have a T-tube probe. Now the T-tube probe is usually a probe located somewhere in the forward portion of the engine cowling, somewhere in front of the fan. And that's what's showing right here. So this is the T2 probe, T2, right here. And we want to make sure that that is heated when it needs to be heated. The heat is turned on by the FADEC. So this probe is controlled by the FADEC of its respective engine. Electrical heating controlled by its respective FADEC. So the FADEC gets its information from this probe. The FADEC, once that probe turned on, it will turn it on automatically, and the system will test itself automatically when the engines are shut down after landing. Now, the caveat here is you only get it tested if you keep electrical power on the aircraft for at least 2 minutes after you've shut the engines down. So you just don't want to land and then get to the gate in 60 seconds and 10 seconds later start shutting the engines down, or the testing will not be done automatically. And what can happen is something could have failed. In the meantime, the next guys get out to the aircraft, they jump in. All of a sudden, they have an alert that says the T-tube probe has failed, or some portion of the system related to the T-tube has failed. And now they're stuck at the gate calling up maintenance. When had you let the test complete itself when you taxied in maybe 35, 45, 50 minutes earlier, or maybe the day before, you would have seen the failure being announced on your ICAS system. Then you could have called maintenance. Maintenance could come out and fix the problem before the next crew took the aircraft, and then everybody would remain on time. So keep in mind, don't turn the power off the aircraft for at least 2 minutes after you've shut the engines down for this automatic testing to be completed. Window heat. Okay, well, this is kind of interesting. Uh, if you remember, we looked at your anti-ice panel, and we had the that line of switches we said are the electrical switches for the anti-ice. Well, the windshield heat is electrically operated. So here we have the windshield switches right here. That's a switch for the left side. This is a switch for the right side. And of course, we have off, low, and high for each of these switches. That's actually an off, reset, and low and high switch. So it's a 3-position switch. So when you put it in low, that is used for defogging. When the switches are positioned too high, it's used for anti-icing. So if you actually had ice on the windows, you could, it's not de-icing, it's for anti-icing. So you're going to want the anti-ice turned on before you get into icing conditions. It's not a de-ice, it's an anti-ice. And during the pre-flight, place these switches in the low position for outside temperatures at or below 30 degrees Celsius. Now, what does that mean? This is a first officer's flow. He's going to set these switches up properly. And in this case, let's say the temperature happens to be 28 degrees Celsius outside. We would look at that because we got the indications on our PFDs, and it would tell us the temperatures. So we're going to sit here and say it's 28 degrees. Okay, that means we're at or below 30 degrees Celsius. So the way I remember how to position the switches, if it's 30 degrees at or below, put the switches to low. So switches to the low position because we are at or below 30 degrees. So there's a low in the word below, isn't it? So at or below means low. That's how I remember. Then all you have to remember is the temperature is 30 degrees. So at 30 degrees, at or below, switches to low. Let's see, I think it's on the next slide, but I'm going to double check before we move on here. Okay, so let me just provide this information to you. Let's see. Yeah, we'll talk about it on this slide right here. So the windshields, the forward windshields, are anti-iced and defogged. So these actually operate with the switches in the low position. And when they're in the low position, you're going to have the forward windshields defogged. If you place the switches into the high position, that is for anti-icing, and anti-icing only occurs on these two windows. These two windows are only going to be defogged. It does not operate on the high position for anti-icing purposes. So forward windows get defogged and anti-iced, and the side windows just defogging only. Window overheat. So this can happen quite often. Let's say you're in Phoenix on a hot day, you're going to have a window overheat situation. Guaranteed, especially if you've turned these window heat switches on low and it happens to be, say, 90, 95, 100 degrees out, you're probably going to overheat your windows. And in that case, what's going to happen is you're going to get an amber alert and nothing you're going to be able to do about it. You're going to take the switches back to off, or eventually when the windows cool down, then the heat will be, the anti-ice system will be restored to that window. But as long as you have right windshield heat displayed, that means even regardless what position you have this switch in, you're not going to have any electrical power or de-icing power to, for example, the window shown here on the right side. So right windshield heat, you can go to off, doesn't matter. Once it cools down, the switch will become active again. And if you don't do something about it, it's going to cycle on and off if it keeps overheating. So follow the QRH in this case. It's a amber alert. So basically you get your QRH out and follow that particular guidance. Window wipers, part of the Canadian thought process here, I guess. The aircraft I flew, they had either two wipers, and each wiper was controlled independently with its own respective switch. Or in the case of, say, the 737, it had one wiper, and both pilots could operate the wiper switch because the wiper switch happened to be pretty much right in the center between the two pilots. So either pilot could operate the wipers off of one switch. In this aircraft, a little different. But to start out with, do not use the wipers at speeds in excess of 220 knots. Now, keep in mind, if you're shooting the approach, which is more likely than not where you're going to be using your wipers, landing in a rainstorm, in heavy rains, you're going to want to operate your wipers. And if you're on the approach, you're definitely going to be going less than 220 knots. So you'll probably be going somewhere around 140 when you're fully configured by the time you get to the final approach fix. So 140 is a good speed to have your wipers be effective. If you're going faster than 220, the airflow across the windshield is actually going to lift your wipers up above the windshield, and the wipers won't be effective anyway. Furthermore, I don't know, I could imagine that if you're going that fast and you're operating the wipers in that kind of wind flow, they could actually get jerked off the windshield and they'd be gone. So limit operation to 200 knots or below. And in most cases, you're going to be well below that when you finally realize that you need to have the wipers on prior to landing. You can also use them before you take off. But just remember, before you exceed 220, you need to have the wipers switches to the off positions. Each wiper operates either from the captain's or the first officer control. So in this case, the captain's side here is captain side, and you have your first officer side over here. Now the question is, whose has priority? Well, it's the last selected position. So let's say the first officer went to the low position because the captain said, hey, give me the wipers on low. The first officer could reach over, switch his switch to low. Both wipers are then going to operate at the low speed. And then if the captain said, yeah, this is not working, and he could just, if he had time, reach over, switch his switch to the high position, then both wipers are going to operate on the high position. So it's the last selected position. Doesn't matter who did it. It could be the first officer or the captain or the first officer's switch being operated last. So that's how they operate. And just as a note, you'll notice that the wipers are parked in the vertical position. So that tells you the engineers are thinking that, the airstream is coming up over the nose like that in that direction. And I would imagine that there's less drag on the wipers, not so much because they're concerned about aerodynamic drag on the aircraft, but they do not want to put too much stress on these wipers as you're flying in excess of 220 knots. So that's probably what they're thinking about. Can't be for sure. That's just my assumption. Ground de-icing. Now, this is not part of your AeroSim modules. This is information I'm providing you because this is where de-icing actually starts. It starts on the ground. We're going to get these aircraft good and clean. It's what we call the clean air concept. It's just something we now do routinely in the winter. We will de-ice, unless, of course, you're south of the Mason-Dixon line. And then those guys down south don't have any idea what ice is. And when they do get it, it's like, holy moly, these people can't even drive on ice. Atlanta gets ice. Oh, look out. Stay off the highways because it's going to be dangerous. But north of the Mason-Dixon line, you are definitely going to run into ice at some point in your career. So get used to it, learn what's going on. The procedures for de-icing aircraft or anti-icing aircraft usually start on the ground. So let's talk about it a little bit. Ground de-icing, ice and snow removal, type 1 fluid. So this fluid that we're spraying on the aircraft to remove ice and anti-ice aircraft is just a glycol isopropyl alcohol mix. Yeah, you can spray it on, it can drop on the ground. Apparently the EPA hasn't figured out that this stuff is somehow harmful to the environment, and it can just wash off into the grass or on the ground. Apparently has no long-term effects. So it's kind of like an antifreeze. It's actually very kind of sweet smelling, and if you were to taste it, it would taste sweet. It's kind of like antifreeze. Of course, you don't want to drink the stuff. That's probably not real healthy for you. So what they do with a type 1 fluid is they use type 1 fluid to de-ice the aircraft. In other words, if it had snow or ice covering the aircraft, say from the night before, or when it came in from a previous flight, if there was any ice on the aircraft, you would use type 1 fluid to remove that ice or snow. It is primarily glycol isopropyl alcohol used to remove ice and snow and frost. We don't even let frost on the upper parts of the wing. That's how important it is to the FAA to make sure we continue to use the clean aircraft concept. We use the de-icing process as an anti-ice when we don't expect any precipitation from the time that we apply this till the time that we get out to the end of the runway for departure. So it doesn't have much what we call holdover property. It's pretty limited. But if it's not snowing, we have no precipitation, we could get the aircraft de-iced, and then we can just let it sit there because obviously it's not snowing. We don't have to de-ice, or I mean anti-ice the aircraft. As long as we can get off the ground, then at that point, the aircraft de-icing systems can take over. So type 1 fluid does not really protect us from further icing conditions, has no significant holdover time. Okay, so we have a holdover time chart. So in the aircraft, when you're in wintertime operations, you're going to have these charts on board that you're going to have to refer to. Either the captain or the first officer will refer to them. I always kind of like to do it when I was a first officer because it kept me in the loop. I was trying to teach myself how these charts work. And the more you use them, the better you get at staying current on them. And of course, every year, the company would come out with new requirements on how to use these charts. So in this case, we're talking about holdover times for type 1 fluid, which this is going to demonstrate it doesn't have much holdover time. Of course, on any of these charts, make sure you read the notes. So in this case, here are the notes. You'd want to make sure you were familiar with how all the notes read. And there are numbers here that identify and relate to, for example, you have a little number 3 here. That would be this note here. And you have 5, 6, and 7 here. You'd have 5, 6, and 7 notes down through here that you'd want to make sure you read to understand what the times and conditions are that related to those notes. Here's a note here, number 10 on other. You go down here, it says number 10, heavy snow, ice pellets, moderate and heavy freezing rain, small hail. And then you'd look down here and you'd see no information, and you'd see caution, no holdover time exists for that condition. So be familiar with the notes when you're going to read these charts. Okay, so let's take a scenario here. Let's see, let me pick one out here. Let's say the temperature today was -5 degrees Celsius. And you had some light, let's see, you had some moderate snow falling. Okay, so it's moderately snowing and it's -5 degrees. So you'd come over here looking at the outside air temperature, you'd come down here and you'd find out that we are going to be right in this block right here, where it says -3 to -6. Then you'd come across and you'd look for the type of precipitation. And in this case, we have moderate snow. You come down and read the intersection point, and this would give you the holdover time for moderate snow using type 1 de-icing fluids. And you can see it only has about 5 to 8 minutes holdover time. Now, when does this holdover time start? It starts at the beginning of the last application of the fluid. So sometimes they have to apply the fluid twice. In this case, if you're de-icing, let's say they had one truck that would normally, the de-icing would normally start on the left inboard wing, and they'd work their way out. Then they might drive all the way around and work their way out on the outboard wing, on the right wing, starting inboard, working their way outboard. So that first time that they start applying the fluid is the start time of the holdover. Now, it might take 5 or 10 minutes to de-ice. Well, you've already exceeded the holdover time. So therefore, you essentially get no holdover time protection with type 1 fluid. I just wouldn't rely on it. If there was any type of precipitation, freezing precipitation, snow, whatever the case might be, I wouldn't rely on type 1 providing any holdover time at all. So therefore, we would want to do what we call a two-step solution, two-step de-icing process. We'll talk about that. So ground de-icing using the two-step procedure. And that simply means that you're going to remove ice and snow using type 1 fluid. Then you're going to use type 4 fluid to anti-ice the aircraft. Now, type 4 fluid is a lot gooier, quite a bit thicker than type 1 fluid. And so to start this process, the two-step process, de-ice with type 1 to remove the contamination, apply type 4 fluid to coat the aircraft with an anti-ice. Note the time at the beginning of type 4 fluid application, because that's your anti-ice. Okay, not the de-ice, the anti-ice. Note the type of fluid and the concentration. So then you go to your holdover time from the charts to determine what the holdover property or length of time you're going to have to get out to the runway after they've completed de-icing. So here's kind of how it's going to happen. You're going to taxi to the de-ice pad. You're going to get a special frequency, and you're going to call up a person on the radio on a discrete frequency, and that guy is commonly referred to as Iceman. So Iceman's usually sitting out here in a vehicle somewhere. Who knows? Say, for example, in this picture here, Iceman could be sitting in this car, and he's looking over here, and he's looking at your aircraft nose number, and he knows who you are because you're not going to tell him your flight number. You're going to tell him this is, aircraft number such and such, we're coming into the de-ice pad. Let us know when we are cleared to approach. And the iceman is going to say, Roger, stand by. And then after a minute or so, he might say, you're cleared into spot number 3. So there was usually numbers painted on the ramp, and you'd approach spot number 3 and set the brakes. And then at that point in time, depending on the company procedures, you may or may not shut down the engines. Most of the time, you'll be shutting down the APU if the APU is running, or you'd shut the engines down and start the APU. Depends on the particular aircraft type. Then he's going to tell you something like, we're going to use a type 1 fluid and a type 4 fluid for a 2-step de-icing process. And you're going to be up there with your pen and paper in hand, writing the information down that the Iceman is telling you. And then you're going to shut your packs off. You're not going to want to ingest this stuff into the pack system, the air conditioning system, so that you contaminate the cabin with the smell of de-ice fluid. So there's a few procedures you're going to learn to use to de-ice, but the big point is that they're going to have trucks out there, the de-icing trucks, that are going to start spraying type 1 fluid on you. When they get done with type 1 fluid, they're going to start with type 4 fluid. And when they get done de-icing and anti-icing the aircraft, Iceman is going to say, okay, type 4 fluid application began at such and such time, say 10 minutes past the hour. And the type of 4 fluid used is, such and such brand, and it was cut with 20 or 30%, whatever the ratio hot water that they're using, or maybe not cut at all. Maybe it's 100% glycol. So they're going to give you the information on that, so you know what you're looking for when you get into the charts in the aircraft. Then once they have said, okay, you are cleared to taxi, you'll go ahead and maybe start both engines up if they were shut down in anticipation of the de-ice process. So it's quite a lengthy thing. It takes about 15 minutes. You usually advise the passengers that they're going to hear some sort of spray hitting the side of the aircraft, and that would be normal. And you're going to try to calm your passengers down, or at least keep them informed. A lot of the well-seasoned veteran travelers are already going to know what's going on, but nonetheless, kind of good to keep them informed. Once you get done de-icing, you would look at your charts based on the information that Iceman gave you and determine what your holdover time is. So in that case, you get a chart out like this. This is kind of a generic holdover times chart for type 4 fluids. And in this case, let's say it's, again, -5 degrees, and we had moderate snow. And we said, okay, that means we're going to fall into this area of the chart here for temperature. Then we're going to read across, and let's take a look up here. Let's say they told us it was fluid was 100% concentration. There was no water added to it. So we would be using this column right up here where it says 100%. And then we would move across, all the way across to where we get to moderate snow, if that was what had been given to us. So there's our moderate snow. And now we have 25 to 50 minutes of holdover time. That's quite a bit. It's giving us a 30-minute window there of no man's land. So we know we've got at least 25 minutes, and we can have up to 55 minutes. So prior to taking off, if we exceeded the 25 minutes, there's a very good chance the captain's going to say, okay, Mr. First Officer, Miss First Officer, go back there and look over the wing and tell us if we're accumulating any snow. That might occur maybe 5 minutes prior to liftoff. So you run back there, take a look, and the passenger kind of look at you. They're kind of giving you the stink eye a little bit, like, what are you doing back here? Aren't you supposed to be up there? And you're just going to inform them Yeah, I'm just checking, make sure the wings are clear. Looks like they are. We're good to go. Then you hustle back up to the flight deck, jump in your seat, fasten up your seat belts, and continue on getting prepared for takeoff. So that's kind of the process that you go through for de-icing and anti-icing. Now, in this case, it says moderate snow. Okay. Well, the problem is you've got to determine what moderate snow is. How do you know it's not uh, light snow or just regular snow or snow pellets? Okay, so moderate snow or whatever that happens to be, we have another chart to look at. So this goes on quite a long period of time, and for each company it might be a little different. But again, you would use all your notes over here. And then you have snowfall intensity as a percent of prevailing visibility. So you'd have to get your ATIS back out. You'd have to say, okay, the ATIS says it's 1 statute miles of visibility. And in that case, you would look over here at the number 1 here, and I'll tell you what, let's just use this ATIS report right here. So I'm not sure what location this is, what airport that is, but they're saying the wind is 160. Actually, the time is 16:20 at this time Zulu. Wind is 150 degrees at 11 knots, gusting up to 17. 1 statute miles, light snow and drizzle. Overcast, 900 foot, -6 and -8. So let's take a look. So we said 1 statute miles. We go up here, look at 1. We come over here and we'd say, okay, we ask ourselves, is it the middle of the day? Well, let's say it was just turning dark, okay? So in that case, we come up here and we take a look at our temperature. The temperature was -6. So this is -1 and below. So -1 and below at night or above -1. So we're going to be following here -1 and below. So in that case, we're coming all the way across here. And it's telling us, based on that visibility at night, at that temperature, that our prevailing visibility or our snowfall intensity is moderate. So if we went back to our previous chart, we would know that we were indeed operating in this column and -6. So it would be again right here. So that's how we determine what chart is what the chart's telling us, what the precipitation rates are. We have to go ahead and get this other chart out and follow through until we figure out what the intensity of the snowfall is. So we just can't look out the window and determine that for ourselves. We use a chart again to do that. Now, that pretty much concludes our anti-ice, de-ice protection on the aircraft. However, here's what I want you to do on your own time. This is one of these videos that I'd very much like to have you look at because it deals with the Florida Flight 90, which departed from Washington National Airport. It wasn't Washington National at the time, but since then, they've named it after Ronald Reagan. So it's National Airport, Ronald Reagan National Airport. I think it was just the DC airport before, but at the time, there was an aircraft, Florida flight number 90, flight 90, was right down here getting ready to take off. And they took off. And if you know anything about the departure here at DC, the White House sits right there. It is. The White House is right there. There's your Washington Monument right here. And in this area is P-50, I think it's P-51, Prohibited Airspace 51. We do not fly into that airspace. They have guns sitting on top of the White House. Will they actually shoot you down? Well, I imagine if the threat became imminent, they would. But when you take off, you're normally supposed to turn and go up the river until you get so many miles out, and then you are clear of the all the prohibited airspace around this little city. And on this particular day, it was snowing. Rather, it was a serious snowstorm. I can tell you that because I happened to be right here as a passenger on another airplane, 3 airplanes right behind Florida Flight 90. And it was an intense snow, heavy snows. And I remember that it was snowing so badly that most of the flights were delayed by around 2 hours. And I had just flown in from Boston, landed here. I had flown in with some lady that had been sitting in the seat next to me. I don't remember what airline it was, but we landed. She had told me that she was heading down to Florida to go to her father's funeral. And I was on a business trip. So when we got off the airplane, she turned right, I turned left. I went to my airplane, she went to her airplane. She was supposed to depart somewhere around like 11:30 or something like that. I was supposed to depart 11:45, a few minutes afterwards. So I knew that if I'm here, she was on this airplane. And I'm pretty certain she did not survive because the only people that survived this accident sat in the tail of the aircraft. And at that time, we had smoking on the aircraft. The smoking people had to sit in the back of the airplane. She did not smoke, so she was not sitting in the back of the aircraft. And the tail of the aircraft broke off, and those were the only survivors. And they plucked them out of the river. Literally, they hit the bridge right here and went into the water right in this area, right about there. Of course, once that happened, they shut the aircraft down. The aircraft I was on went back, and I remember it parked right in this area somewhere. We got out, walked back in. The airport is shut down, and so it's probably going to be shut down for the day. So everybody tries to exit the airport, and the metro system ran through here somewhere and did one of these kind of numbers. And that day, the metro system, right after this crash, jumped the tracks over here somewhere. And a couple of people were killed on that thing. And then the metro system got shut down. So everybody at the airport was trapped at the airport, couldn't go anywhere. And then finally, some of us realized that, oh, hey, we can get on the metro. They're running the metro from this point over to here and back and forth. And that's what they did. So we all got on the metro. It was a free ride. We could get over to this side of the river. We could grab a cab and get to wherever we needed to go downtown Washington, D.C. to try to get a hotel room or whatever the case might have been. But anyway, it was a disastrous day in Washington. And I suggest you watch this YouTube video. Just copy and paste it up into your browser, and it should come up. But really a good video to watch. It talks about the issues with icing. This particular accident got the FAA on board with really getting proactive about de-icing aircraft, and that's where we get the clean aircraft concept from, that we do not take off with frost, snow, ice, nothing adhered to the wings. We can take off at this stage of the game with a little bit of frost on the bottom side of the wing, but nothing on the top. So watch that video and hope you enjoy it. It's got a lot of good informative information, historical information that you will be able to brag about knowing to your fellow pilots somewhere down throughout your career. And that's that. So this module is complete. That's our ice protection module, how we operate the aircraft in icing conditions. something you're going to go through every year, especially if you're flying north of the Mason-Dixon line. In the meantime, go to your module. If you complete it, make sure you sync the module so that I know that you have completed the module for that point for the class. And until then, I love my job. Glad to be here. Hope I can make a difference.